Hey everybody, Dr. A here, and in this video we're going to be providing some background information on particle equilibrium, and in particular we're going to be focusing on the background information involved with two-dimensional or 2D particle equilibrium. So before we get started on this background information, please don't forget to hit like and subscribe and be on the lookout for all kinds of content related to this. So let's go ahead and get started.
In this video, we are beginning the next chapter of our course, which is Chapter 3. And Chapter 3 deals with equilibrium of a particle. So in this chapter, we're going to be studying particle equilibrium in both 2 dimensions and 3 dimensions. Now, two-dimensional particle equilibrium should be somewhat familiar to you. You probably dealt with this to some degree or another in Physics 1. But we are going to kind of go a little deeper into 2D particle equilibrium. And then often 3-dimensional particle equilibrium is new to everyone at this stage. So let's go ahead and get started. So in this case, a particle will be modeled as a single point. So it'll look something like this, like a dot, okay? And will be at rest, okay? So when we say equilibrium, we generally mean at rest. So what this implies is that, we're going to say this implies that the sum of the forces acting on that particle equals 0, all right? So that means we're going to say summation of all of the force vectors acting on a particular particle equals 0, all right? And that's generally the, how we think of this. Now, when we do these numerical problems, the first thing you want to do is draw a free body diagram, all right? So we're going to say always begin the computation process by drawing a free body diagram. I cannot emphasize that enough. The majority of the mistakes I see people make with these problems comes from either they're not drawing a free body diagram at all, or they're drawing a free body diagram incorrectly. So let me tell you what is involved with a free body diagram. A free body diagram, or I'm going to abbreviate it FBD, is a diagram showing spelled showing wrong, forgot the N, showing all known and unknown forces and measurements on the system, okay? So any angles, any slope definitions, any lengths, all of that information needs to be incorporated into your free body diagram. And when we get into some numerical examples, you will see how we emphasize why this is so important, okay? So the next thing we want to talk about, just to kind of lay the groundwork, are what we call types of particle connections. Okay, now a lot of these you've heard of at some point or another. One type of particle connection is a cable, okay? Cables / ropes / wires. They all, from a statics perspective, whether it's a cable, a rope, or a wire, they're all pretty much, they behave the same way, okay? And here's how we, what the assumptions are of cables, ropes, and wires, okay? We assume no stretching, okay? We assume no stretching. We assume they have negligible weight. Okay? And we assume they only support tensile forces. Now, that's a big one. If you think of a cable or a rope or a wire, we're assuming that they can only support tensile forces. Now, let's think about if that makes sense. Well, if you have a rope, for example, if you tried to push on a rope that was just sitting somewhere, sitting on the ground or sitting on a table, what's going to happen? Well, that rope will tend to just kind of crinkle into itself. It's not going to support that force. Okay, but what it can support is a tensile force, which is a pulling effect, right? If two people pick up a rope and they start pulling in opposite directions, it will support that force. And that's how we got the game tug of war. And cables and wires behave in a similar way, okay? And the next type of particle connection that we may deal with is a pulley system, okay? So we're going to say pulleys, all right? Now, how do pulleys work? Well, pulleys are typically drawn kind of like a circle, and they end up having a cable or rope wrapped around it somehow, okay? Now, those pulley systems have a constant tensile force support throughout the entire length, okay? So for pulleys, you have a constant tensile force throughout the length, okay? So those are two common sets of types of particle connections. Now the last one is going to be springs. So I'm going to write over here springs. Okay. So for springs, we assume that they can stretch. I spelled stretch wrong. Stretch. Now, how do they stretch? Well, the stretch is governed by Hooke's law. Now, you may remember from a physics class Hooke's law. What does Hooke's law state? Hooke's law says that the force in the spring is equal to a spring stiffness, which we typically call K, times the stretch of the spring S. So we're going to say K is what's called a spring stiffness, and S is the spring stretch, which is equal to the stretched length minus the original length. Okay, so I'll put a note here. This is the stretched length, and this right here is the original length of the spring. Okay, so for example, let's say that we have a spring here with nothing on it, and then at some point later we take that spring and we put a force on it, F. Okay, so this length may be L naught, the original length, and then this length is the stretched length. And so the difference between the two right here, that's S. That's the spring stretch. Okay, so these are situations that we're gonna kind of come across both in 2 dimensions and 3 dimensions. By the way, we are going to start with 2-dimensional systems, but we're going to quickly apply these same concepts in 3D as well. So let's first start by talking about 2-dimensional, or sometimes we call this coplanar forces. Okay, coplanar means within the same plane, which a plane is 2 dimensions. So again, for equilibrium, if we have the sum of the force vectors equals 0, specifically equals a zero vector, what does that mean? That means that the sum of the forces in the x direction times the I component plus the sum of the forces in the y direction times the j component equals a zero vector. Now, what does this imply about each one of these pieces right here? This implies that the sum of the forces in the x direction should equal 0, and the sum of the forces in the y direction equals 0. So what we call these two equations right here are called the 2D particle equilibrium equations. So when I say, if I ask you the question, how many equilibrium equations do we have for two-dimensional particles? You say we have 2 of them, and here they are. Sum of the forces in the x direction equals 0. Sum of the forces in the y direction equals 0. Okay? Now, our sign convention, so let's talk about that. Our sign convention typically states that we call things pointing up positive and things pointing to the right positive. Okay, that's what we say. We say things going up are positive for y directionality, and things pointing to the right are positive for x directionality. Okay, so that means if you have something pointing to the left, when you're doing calculations, it's going to have a negative built in somewhere. All right. So the way we would set this up is we would say sum of the forces in the x direction equals 0, and we typically put a little arrow on top of that sigma and f symbology, and then we would say sum of the forces in the y direction equals 0, and to the left of the sigma and the f sub y, we put an upward arrow. And what this is telling us, this is telling whoever's looking at your calculations that all of your calculations are based on force components pointing to the right are going to be a positive value, and force components pointing up are going to be a positive value. So anytime there's a negative, that means that if it's horizontal, it's pointing to the left, and if it's vertical, it's pointing down. All right. So the next thing we want to talk about is how do we handle unknown forces? So like, what if we were asked to solve for a force? How do we handle an unknown force if we don't know what direction it's pointing, for example? So I'm going to say for unknown forces where we do not know the magnitude or direction, we must assume a direction. You have to assume it's pointing somewhere, okay? So here's what we typically do. Here's what we recommend. We recommend that unknown forces point away from the particle in the free body diagram, okay? And then what'll happen is when we apply equilibrium equations, if the unknown force is computed as negative, then it is actually pointing in the opposite direction of what is assumed. Okay? So I know that's a lot of words right now, but once we do some numerical examples, we're going to illustrate this concept. So again, when you have an unknown force in a free body diagram, you just go ahead and assume that it's pointing away from the particle when you draw the free body diagram. And then once we do the calculations, if that force is computed as a negative number, it turns out it will be pointing the opposite of what you assumed, which if you assumed it's pointing away and it's negative, that means that that force is actually pointing at the particle in the free body diagram.